Okay, we're talking about the standard normal distribution. The standard normal distribution has a mean of 0 and a standard deviation of 1. All of the data values in this distribution are their own z-scores. The area under the curve here, the probability density function, would be 1 or 100%. If I go out 1 unit from each side of the mean, then I've gone out 1 standard deviation. If I go 2 units from the mean and up to 3 units from the mean, I will have accumulated almost all of the data according to the empirical rule, because under a normal distribution or mound-shaped distribution, almost all the data is within 3 standard deviations of the mean. Approximately 68% of the data is within 1 standard deviation of the mean. So the area under the density function above the interval here from -1 to 1 should be approximately 68%. Now, to actually calculate that value from the standard normal table, the standard normal table gives us the area from 0, or the location of the mean, out to any z-value, any positive z-value. It gives us the area under that density function, or the probability. Now, what we would like to do to verify the empirical rule using the table for the 68%, empirical rule says that approximately 68% of the data is within 1 standard deviation of the mean. So I'm looking at the interval from -1 to 1. So I want to go to the table and I want to calculate the area from 0 out to 1, because again, the table only goes from 0 out to positive z. So I want to find this area or probability. So I need to go to the table and look up 1. Problem, I've got this z value equal to 1. So looking up the z value, go down here, z is 1, I get 0.3413. So this area from the center out to z is 0.3413. So going back here, this area is 0.3413. But I want the probability of being within 1 standard deviation, so I want to include also this area to the left. Now, because the distribution is symmetric, in other words, the right side and the left side are sort of mirror images of one another, I can see that going an equal distance on each side would yield the same area. So the probability of being within 1 standard deviation of the mean, I would add these two together and get 0.6826, or approximately 68% of the data. Let's try another one. The probability that z is less than or equal to 2.18, or that z is in the interval from -infinity to 2.18. Okay, to find that probability, I want to look at the density function. The area under the curve of the density function over the interval is the probability that z would be in the interval. Okay, so how do we get that area? That'll answer our question. I'm going to need the standard normal table to do that. So I'm going to look up 2.18. Notice that the standard normal table will give me the area from the center out to that 2.18. So looking up z equal 2.18. Now 2.18 is 2.1 plus 0.08. So for z, I'm going to go down here to row 2.1 and then over to column 0.08. So looking along row 2.1 and then over to column 0.08, I see 0.4854. So going back here, standard normal goes from 0 out to my z value. So this part of it is given by the table. 0.4854. Well, that's not all. I've got to get the piece to the left of that. But notice that the table goes from 0 out to z. 0 cuts this distribution in half. Each side is a mirror image of the other. The probability or area under the entire curve is 1. So the area to the left of that line, in other words, this whole shaded area, must be 0.5. So the answer to my question, to get the entire area or the entire probability that z is less than 2.18, it would be 0.5 plus 0.4854 or 0.9854. So the probability that z is less than 2.18 is 0.9854. Okay, let's try the probability that z is greater than 0.84. Okay, so my interval now is 0.84 to infinity, and the probability of being in that interval is the area under the density function above the interval. So I need to find that area. Standard normal table is what I've got to use to calculate any of these areas. So I'm going to be looking up z equal to 0.84. Again, remember that the standard normal table will give us the area under the curve from the center out to z. That's not what we want, but we can use it to get what we want. So let's let z equal to 0.84. That'll be z down to row 0.8. 0.84 is 0.8 plus 0.04. So going to column 0.04, we move along and find the value 0.2995. So from the center out to z, we get, from the table, 0.2995. That's not what we want. We want the area under the curve from 0.84 to infinity, to the right, that green shaded area. So how are we going to get that? Well, we'll use the idea that this is a mound-shaped distribution. It's symmetric through the center line there. The total area under the curve is 1, so the area to the right of that vertical line is 0.5. The area to the left is 0.5. So this red shaded area plus the shaded area that I want has to add up to 0.5. So to get the area or the probability of being in the interval is going to be 0.5 subtract 0.2995. And that will be 0.2005 or 20.05%. That would be my answer. Notice something else. If I said the probability that z is greater than or equal to 0.84, will that change anything? The only thing that changes is it adds a point into the interval. So up here I would put a blue bracket indicating I'm going from 0.84 forward. But that really won't change the probability, because the area under the density function above a point, well, it's just really a line. There is no area. The probability that a continuous random variable takes on any particular value is 0. So the answer here would still be 0.2005. Okay, let's find the probability that z is less than or equal to negative 1.75, or is in the interval from negative infinity to negative 1.75. And so we'll go to the density function, and negative 1.75, so maybe about right there. And my interval starts there and then goes down to negative infinity. And I want the probability of being in that interval, so I'm looking for that area. Now, what I'm going to have to end up doing, the table only has positive z-values. So I'm going to have to look up a positive 1.75. So looking up a positive 1.75, let's see, that would go down to row 1.7. 1.75 is equal to 1.7 plus 0.05. So I'm in column 0.05, so moving across there, I have 0.4599. 4599. So let's go back. And that actually, remember the table gives you the areas from the center out to your positive z-values. So looking up the 1.75, I found this area, and that would be the 0.4599. Now, how am I going to get the area I want? Well, again, the distribution is symmetric, and cutting it right down the center there, I know that the entire left side is 0.5. I also know that going the same distance out from the center, that this area right here that I'm shading is also going to be 0.4599. So to get the area that I want, I'm going to have to subtract that from 0.5. So the answer is 0.5 subtract 0.4599, which would be 0.0401. Probability that z is between a negative 0.32 and a 1.49. So let's get a picture of that in the distribution. Center at 0, so about a third of a standard deviation to the left, maybe about right there. So that's the negative 0.32. And then my interval on the upper end goes to 1.49, maybe about right there. So my interval here, and then I want to get the probability of being in that interval, so that's the area under the density function above the interval. Now I know when I go to the standard normal table, I can only look up positive values, but because of symmetry, if I look up the positive 0.32, I would get the area to the right, which is going to be the same as the area to the left, because 0.32 is the same distance to the right as negative 0.32 is to the left. So if I go and look up 0.32 in the table, so I have a 0.3 plus 0.02, so 0.32 would be a 0.1255. So this area here would be 0.1255. Next, I'll look up the 1.49, and that table value will give me exactly the other part of this. Because again, the table measures out from 0 to the positive z value. So I want to go to 1.49, which is 1.4 plus 0.09. So looking across there, all the way to the end, I get 0.4319. So 0.4319 will be this other part here. And then my probability would be, I would just add the two parts together to get the total area, or the total probability. So that's equal to 0.5574, or 55.7%.